Alright, sorry for the delay. It's some technical problem. But now we're here. My name is Simone Totaro, and I am a research intern at UTF, the AI Machine Learning Lab. And there are a bunch of friends here coming from the same lab. My main interest is in reinforcement learning. I'm not going to talk about this today. But let's say, what I do when I don't work as a researcher, I try to add one more A in front of AI, which is applied. And that's the source of this work. This is coming from consulting work that we have done. And our client agreed to give this library open source, and that's what I'm going to talk about. Alright, so first of all, why this library? The first thing is that deep learning is becoming complex and more complex. And it's very, very easy to compute not code mistakes, but statistical mistakes. So the things that you try to measure, they may be wrong. And it's kind of boring. Like if I come from another field, for example, say biotechnology, and I want to apply deep learning models, then doing TF layer dance 20 times, it's a pain. Okay? And guys, life is just too short for bad code. I'm not saying that my code is good, but I found things like this. Mashing around different kind of models. This is actually, it's a very important research that's been published, I think, less than a year ago, and it was about medical studies. And there have been many things in this research that make me, let's say, question how the results are, let's say, repeatable if you want, or you can agree on that. Okay? So, having said that, I think we can start. First question, how many of you have tried or played with time series? Right? Cool. How many of you have tried to play with time series and deep learning? Alright? And deep learning by themselves? Okay. So, my goal for today is just to make you understand what is the difference between doing time series regression and classical supervised learning between cats and dogs. And second thing is that if you go home tonight and if you find a library that you like, you find some data that you like, you try to hack it, then hack it. Okay, so the outline is more or less this one. There's going to be a little bit of math inside, so just giving you a word. If you don't understand something, just raise your hand and stop and here. I'm assuming that you know how deep learning works. I'm not going to go through the ideas. Alright, so the first thing first, that a time series is defined as an ordered sequence of events that we're trying to measure. Hopefully they are evenly spaced, so we don't have missing data between time steps. And we assume they are coming from a geometric process that is giving us some data. Example is the stock market. We observe those prices at each time step, and we know how it's performing, or the temperature, or things like that. So we have a function that is indexed by time, and maybe can be a function of past values, but not necessarily. A more general case of this is that if we have some feature X that define our process or the outcome of our process at times. This is in the setting, it's called multivariate regression if you want, and the multivariate part comes from adding different features, but not by predicting more values or predicting a vector or metric in Y. Y is just a real number that is indexed by time, and is given by these past values, those features, and the time that we want to predict. Alright, so I give you some data. Okay, this is very standard. Suppose there are data here. Can I just throw deep learning right away? What do you think? Can make it work? Who says yes? Okay, that are complete, they are fine, they are cool, they are cleaned. Okay, give you those data. Can I apply deep learning right away? Who says yes? Okay. Who says no? Alright. No. You can't. Now the important answer is why you can't. Usually, I mean, when we do supervised learning, we assume, okay, those are supposed to be not there. Anyhow, so when we do supervised learning, we assume that our data comes from an IED distribution. The idea is we have some distribution our data, and we try to let's say make an estimate of xi. And in this assumption, what is working underlying is this law of large number. That basically tell us that the empirical mean, so 1 over n sum of all x's, is going to converge to the true mean of the distribution. So if you have a Gaussian and you sample from this Gaussian, the sample that you get, if you sum over and you divide, you get the true mean of the Gaussian. Now, is this true? Well, no, because our sample are not independent. I mean, we observe these time series, they are evenly spaced in time, and actually what we actually want to learn is the dependence between those samples. So this assumption doesn't hold anymore. And the second thing is that they might not even be identically distributed. They might come from whatever distribution you got as well. All right. Another GIF that went. Okay, so it was still another GIF that wasn't there. So the geometry does not hold. What we can do about it? Well, we have a concept that is called stationarity of a time series, and that is what is, let's say, it's a very strong concept that is telling us that the mean that we measure in our data does not depend on the space in which we measure this mean, but just on the line. Suppose I measure a mean between observation 0 and observation 10, and then I measure between observation 10 and observation 20, that has to be the same mean or the same variance. That's what we call stationary moments. The first moment is the mean, and the second moment is usually called, it's actually not variance at the moment, but it's related to the variance. And that's what we actually require. And this should be the main goal of your preprocessing when you deal with time series data. You should make sure that you get that stationary distribution after applying some filtering, after doing some statistical tests, but that you work with those data that have these properties. How can you measure them? Well, you can look at the correlation between the data, which is the linear, let's say, dependence, okay, between data at different time steps. You can look at the covariances, you can look at this parallelogram, or you can go in the frequency space if you're familiar with it and play with some Fourier transform and so on. Good. So, question? Okay. Good. Okay. Finally. Okay, this worked. Good. We have our stationary series. Now we can throw our deep learning machinery to it, and we can try to learn f or p or the function. Okay. So the task of learning the setting can be phrased in different ways, and one of them, or the way in which I treat this library, is that I'm going to give him some past data, some history, and I want to predict or forecast the next k values of it. And this usually is done, at least in this framework, using this minimization of some loss function, using some gradient method, whatever you want. But the idea is that if we take the gradient of this loss function, it's going to give us a direction of where the minima is, and we can adjust the way the parameter of the estimator in order to get good at this. Something like this, I believe, if you've done TensorFlow, you are familiar with it. We have some layer, the dense layer is going to get an input, it's going to give us 1 unit because y for us is 1. Then we try to reduce the mean and we apply an optimizer that we equate to this. Simple as that. Cool. Now, the first, I think, important question for me becomes, okay, well, what kind of loss function should I optimize for? There are many of them. There's a huge literature about it. Usually you find this mean absolute error, which basically measures the distance between your prediction and your real value in an absolute sense. you also find this mean average percentage error, which is another way of, say, capturing the trend. And also recently came out this, well, say 10 years ago it came out this dynamic type wrapping that is written like this. It's called soft dynamic type wrapping. For 10 years it's been just dynamic time wrapping, but now they make it soft. And the soft part is important because now it's differential. So we can take a gradient out of it and this gradient makes sense. Most of the time, for example, the MI is not differentiable, but we do it very well. No, actually it's important. Okay, so what is, I advocate for this loss, it was a pain to actually make it, it didn't work, but I advocate for this loss because it has some principle idea. The idea is to find the shortest path in order to align the two time streams. Suppose I observe the red line and I'm building the blue line, which is my y hat, and my goal is to minimize the cost to align the two lines according to some distance that I choose at the beginning. And then I cannot show you this down, but you can see the difference in the result. Okay, mathematically speaking, this is what's up. So you have your y, you have your y hat, you have this matrix A, which is it's a matrix of 0, 1. This is going to tell you what is the path that you compute in order to align the two series, and you have this nabla, which is telling you. Sorry, this is not nabla. It's the distance matrix. That is going to tell you how much you have to pay in order to align the two series. Good. Okay, now how do you pick a loss function? Well, there are many ways of doing it. The first one, that's the most principal one, is you think about the class data that you have. If you have, I don't know, financial data, then you may want to pick a loss function is going to capture the trend of your data, because that's what mean absolute error is doing. If you have some signal like EEG or something, you may want to capture the exact variation of each time step, then even by this dynamic type wrapping cannot loss. Otherwise, if you have interns, you just throw interns at them and it will eventually solve itself. As I said, some loss functions are smooth, like this MAME, these are soft dynamic type wrapping, some others are not. Smoothness is nice to have most of the time. Sometimes, I mean, again, we have a very powerful approach philosophy that we need here, but it's important. Okay. Questions so far? I think I'm going very fast. Okay? And the question will go on. Okay. I'll take this. All right. Okay, so let's look into models. Now, even in this setting, it's very important to understand what you're trying to achieve from your data. Suppose you have data that have very little correlation between them, then maybe even a fully connected can work out. But if you don't, if you have data like, I don't know, you're analyzing music or things like that, then you need to have something that can memorize your data, that can remember things. Or something that can, for example, approximate the stochasticity in your data that depends on something you're not observing. So suppose you are measuring the temperature in some agriculture field, and there is some weather problem, but you don't observe it. So you need a way to capture this stochasticity, this random process that you do not observe. And this has been done for years with some models called Gaussian processes. They are very powerful, but they're very, let's say, they scale pretty bad. And let's say less than maybe a year ago, this came out, which is conditional process, which is kind of a son between the baby between the neural networks and Gaussian processes. That seems like it's working very well. And I mean, you don't find the thing otherwise in the GitHub. It's on just on at least. Good. So, All right. Spoiler! Spoilers. Okay, that's cool. Okay, so recurrent neural networks, how they are built. Well, usually, again, I mean, they are different from dense layers. And the main difference is in this, let's say, H tilde, if you want. And this is, let's say, sigmoid in the middle. Basically, we have an internal, if this and that is very smart, it is telling us what we should remember, what we should forget. In this particular setting, we have xt, which is our input, and it goes through what is called gate in the deep learning algorithm. And we are going to, for those gates, we are trying to, the cell has to learn what to remember, what to not, and it's going to keep a state, like a state machine that is called ht-1, that is going to be passed to the next iteration of this enrollment of the cell. Okay. Usually, I mean, you can probably stop here if you're building a recurrent neural network by itself. So you just add your historical data, x1, xn, and you pick the output of the encoder. That's already enough sometimes. Sometimes you need something which is a little bit more heavy, and it relies on the assumption that you have sequence clear. And this is exactly what an encoder decoder does. This has been introduced for the first time in the context of neural language processing, where you have a long dependency in data. We also do have a long dependency in the series. And the main idea is that we pick the last encoder state and we use it to generate the next series. Now, the feature of this model is that you can generate your series as long as you want. Once you fix an encoding state, you can unroll your decoder for as long as you want. And that's why it's also called a generative model, not just a standard say, encoding or recurrent Two things to notice. The first one is that we have this encoder state that is passed between encoder and decoder. We can do something with it, and usually what people do, they build attention on it, attention mechanism. That means attending to some specific feature of what we are encoding. So we pick some feature of the encoder, we try to see if we can use those features in the state of the decoder, and if this is so, then we can condition the output of the decoder at some time step with respect to the feature of the input. It's kind of a tricky. I think that I have slides for the last part, but it's a little bit tricky. The other thing to notice is that, as I was saying, this is all a deterministic process. So we get data in, we get it out. There's no randomicity in the learning process. It's just in your data. We can do something about it, and this is exactly the class of model I was telling you earlier on, which is called those neural process. And the way in which they work, they split. So what they're trying to do, they are trying to approximate functions over your dataset, or a class of functions over your dataset, not just your y hat, if you want, but the whole function over your y hat. And that means that it's going to also give you as an output not only the mean, so not only the value of your y hat, but also the variance of it. So how is certain with respect to the prediction of speed, which is a very nice to have, but this means. How does it work? Well, you pick your dataset, your x, you split it in training, you split it in context and total points. You don't change just in context. You pick some of them. You train your encoder. You can see this as an encoder. This is going to output some statistics, which is the aggregator, which is a mean, over the feature axis. So you keep the time axis, say, it's full. And then you use this mean to build the output time series according to some x total. That can be, for example, if you have, suppose you want to make prediction of, you know, Thursday time at 3, you can do this through this x. And they are very powerful, at least in my opinion, and the reason is because they also, again, give you a variance estimate of what you're trying to estimate, which is pretty neat. I mean, if you have to use the thing for for decisions, so you actually want to know how it is done. The little issue with this is that it's very old. Like they are not so, there hasn't been made so many tests, and sometimes it might emerge, might not. It's tricky to. For example, if you try to replace that encoder with something more fancy, for example, convolutional nets, then things become harder and it may not even convert. It's not that easy. But if you have just fully connected, it performs really well, and you get your fairly good prediction. Cool. Now the other difference is that here's what the, if you want to, is what the stochasticity captures, that at the same time we compute the log likelihood as a loss function instead of the loss function that showed before, like the MNC or the absolute error. And at the same time we just get the variance in the mean of our function. Good. Alright. Now, there is an elephant in the room, and it's a very big, because at least in the time series setting, like there is no clear reason on how you evaluate if your model is good or not. You can capture data set deterministically, pick some points and try to predict them. But if your time series is particularly, stationary at that point, or maybe has some seasonality inside, then the estimate doesn't really work. You can do some daily sampling, you can do some constant split, and this really boils down to application-specific cases that I cannot cover, but be aware that testing is very important. You can get completely different models out of our human testing. Good. Questions? Like, I'm done. Like, seriously, this is the last GIF, almost the last GIF. And if you have questions, this is the time.
There was a couple of slides ago, an image before this one. GRU, I don't understand.
So this is a cell. So this encoder, the encoder is built around this small cell, which is actually it's a neural network. So instead of being this is the group that you see. This is exactly the unit that you use in order to build them. You have just one of them, and you roll it over time. You make it the input pass again through like a fourth cycle. You do this. You iterate over the length of your sequence. You have 24 steps. And you evaluate the cell, and you call the cell method 24 times in order to get 24 estimates at each time. And this is the process called enrollment, and that's what you see from X1 to Xn. You iterate over these n steps, and at each step you ask the same cell, hey, I'll give you the state of your past estimate, and I'll give you the new data. Can you tell me what is the next value that I should out?
Here, I don't know if I understood what the color is like for data dimensionality to reduce the data, or it comes in chunks, or what is the reason of the color? Because sometimes.
Yeah. Okay. So well, the reason of the encoder is to extract features. The more you can.
Reduce, it's like an autoencoder or something.
Yeah, exactly. I mean, no, the autoencoder is a different thing. In the autoencoder, you are trying to rebuild your output. Okay.
Yes.
So if I cut here this graph and specify a loss function saying, give me your feature, and then with those features, try to minimize the reconstruction error, or try to rebuild the data that they give you, then that's an improvement. In this setting, we don't have this part. We just want to extract as many features as we can, and they have to be as expressive as they can. But we cannot control it directly, or at least this is not usually done.
And that directly is not.
No, usually we control it through the loss function of the prediction, because we assume that if we optimize that loss function, then the whole process should be optimized. One thing that I can tell you is that there is a new attention mechanism that is called input attention mechanism, and you find it in the library. That is basically it's adding a fully connected layer here, and what it's going to do is to evaluate how important are your input in order to weight them accordingly let's say at the encoding time. Okay. Yeah. Okay, so okay, so there is some for this model we don't have the deal. We don't. If you want a theoretical answer, it's a strict one. You have to make sure that this model are very prone to refit because you have a lot of unit, you have a lot of weight. But eventually, it has been shown that gradient descent works as a regularizer. And so somehow even if it's over-parameterized, it allows you to converge to something that is useful for prediction. Yeah, honestly I try to keep the number of units as low as I can. So once I overfit my model, then I destroy the number of units and try to see if I can get the highest.
I didn't see from the library what benefit gives with respect to
That's a question that I would love to answer without, but I can't. So there is I can I use your. So, this is the library itself. What is the benefit? Well, it has a bunch of models that I wrote. I picked them from papers that they revealed, challenges on cargo in some cases. So those are all models that I've been running testing for. They have been somehow certified in the paper. Sometimes I also go to the author, say, hey, did you want to actually do this part of code? So those are models that at least I spend a lot of time in making sure that they are correctly used and they're correctly implemented.
Okay, so
that's the first thing.
I don't have to choose the loss function. You know that
I give you some loss functions that you can pick from. I give you some models that you can pick from. They're already pre-made. You just have to give me a data set that you want to get your estimates from, and that's it. That you run a Python command, you do your training. I give you something that I don't know if I have it here. No, I cannot show it here, but I'm going to give you a folder with all the logs, the results, and so on and so forth, and some fancy picture and some checkpoint where you can reload your model, for example. So this is the main thing. This commit is pretty old. I have to push new stuff. But again, there is another elephant in the room, which is TensorFlow 2 is coming up. That means that I have to rewrite everything with the eager execution enabled, and it's going to take me some time. So if you want to use the library, or if you're interested in this stuff, write me an email, which is going to be here. Write me an email, say, hey, I hate your work, I hate your code, I want to help. I'm going to have a coffee, and I'll be happy to show you like how that works and what we can do together. I really prefer this way than just cloning the library, because either it's not going to work, you're going to have problems, I have to push a Docker, like it's still a very big version, and now that I'm working with the session, I have even less time. So if you're interested, just ping me, and I prefer to have a coffee and then a chat. Okay?